Hello friends. So again I am back. So this time I have come with a lecture on Mohr Circle. One of the very important concepts in strength of materials is the concept of principal stresses. And this Mohr Circle is related to principal stresses. Rather, it is a graphical method to find out principal stresses. So let's proceed with the lecture. So talking about principal stresses. So principal stresses occur at principal planes. And what are principal planes? These are the planes at which there is no shear stress, and the stresses determined at these planes are known as principal stresses. So now the question is, why do we need to find out or to determine principal stresses? Because uh, as a being a mechanical engineer, we design machine components, a lot of components we design. And when you're designing some component, so you should have the maximum value of loading acting on that component. Now, load can be of different types. The load acting on the component, the external load acting on the component, it may be axial load, it may be a bending load, or it may be torsional load, or the combination of these loads. So when we have complex system of loading, so in that case, it is quite difficult to find out the maximum stress. So using the concept of principal stresses, we can get the maximum stress. Actually, we get a range of stresses, the maximum and the minimum. So we get the stresses at the extreme. So which is very helpful for a designer uh, in designing various components. So when you talk about principal stresses, so let's say we have here sigma, and sigma is a symbol normally used for normal stress, and tau is the symbol used for shear stress. So here we have taken normal stresses along or in the x and y directions, and shear stress. So let's suppose they are acting on an element. So this is an element. So here you can see the normal stresses acting at in the x direction. This in the x direction, sigma x. This is sigma x both ways, and this sigma y. So you can say on the x and y faces we get normal stresses, and they are tensile stresses. Similarly, we have shear stress acting across the edges, tau x y. So these are the stresses which we can determine. So these normal stresses, sigma x or sigma y or tau x y, these stresses uh, can exist because of axial load, bending load, and torsional loads. So these are the stresses which we should have in order to find out principal stresses. So as shown, sigma x star y star, that star superscript has been used just to differentiate. So as you can see in the figure, these are x and y axis. So what we are trying to do, we will try to find out the value of these stresses at new axis, which has been rotated at certain angle theta with respect to the existing x and y axis. As an example, you can see in the figure. So these are the new axes. So the element has been rotated just to make things quite simple to understand. As you can see, the what we have in our hand is sigma x, sigma y, and tau xy. Now we need to resolve these three stresses along the new position, which is at an angle of theta. As you can see in the figure, the x and y axis has been rotated counterclockwise at an angle theta, where we get new axis, that's x star and y star. So in order to find out the stresses with the star superscript, we need to resolve sigma x, sigma y, and tau xy along these two axes, new axis, that's x star and y star. So when you resolve along these two axes, what we get? We get normal stress in the x direction, but this is with superscript star. That means in the newly rotated x direction. So this is the equation. Similarly, in the y direction, and the new shear stress. So from these three equations, we realize that in case we need to find out the normal and shear stresses at some axis which has been rotated at certain angles with respect to the initial origin axis. So we have to make use of these three equations. So sigma x, as I told you, sigma y, these are the normal stresses which we can determine, and tau xy is the shear stress. So we shall remember these equations. These are the mother equations, generalized equations. So just summarizing, so what we did just now, what we learned that with the given sigma x, sigma y and tau xy, we can find out the normal and shear stresses at any newly rotated axis. So let's move ahead. So now about principal stresses. Now the basic definition, as just we have discussed, the definition of principal stress is that the stresses which are calculated at the principal planes or the principal axis. Now what are principal axis? How to determine the location of principal axis? So at principal axis there is no shear stress, or we can say the shear stress is equal to zero as shown in the on the slide. So if you put this shear stress equal to zero, what we get? We get this formula. So that P subscript has been used just to symbolize the principal axis. So determining the principal axis means find out this angle theta P. As in the previous slide we have seen, I will just try to show you once again here. These are the initial axis. Let's say this is the x axis, and this is y axis. So now theta P means what? As we have learned, if we take new axis, say x star, as we have taken the previous slide, we have discussed that at an angle of theta. This is, let's put theta. Now we can find out the value of this stresses about this new axis, that's x star and y star axis. So in this rotation there will be a value of that theta at which you won't get any shear stress. So at that point what we get? We get the principal axis, so which can be calculated using this equation. This equation can be used to find out the location of principal axis. So now what about principal stresses? If you take this value of theta p and substitute this value in the previously discussed equations of sigma x and sigma y, so what we get? We get this equation. Sigma max, one of the principal stresses, and sigma minimum, second principal stresses. This is difference of plus and minus. This is here you get plus and you get minus. So these are the principal stresses, extreme stresses. So these stresses, sigma max and sigma minimum, you get at an angle of theta p. So once again, this is summarizing. We started with an element about which we can find out or at which we can find out stresses, normal stresses and shear stresses along x and y axis. Then we rotated those x and y axis to some new location, so which was shown by a superscript star, and at those axes we have obtained generalized equations. You put for the value of theta, you will get the value of normal or shear stress. Now in the same rotation, while in the same rotation of angle theta, so there comes a value that's called theta p at of the axis at which there is no shear stress, and from this equation we can find out that location. This is theta p. It means at this theta p you get principal axis, and if you put for this theta p in the previous equation, you get these two equations, sigma max and sigma minimum. These are the principal stresses. So in total we have previously three equations, and here 4, 5 and 6. So these 6 equations must be remembered. So let's move further. Let's see what comes next. Now this was all about maximum or minimum normal stresses, because when you talk about principal stresses it refers to normal stresses. But what about shear stress? Can we have maximum shear stress or not? Yes, So there can be a maximum value of shear stress, and this is the angle. The maximum value of shear stress, or the axis at which shear stress is maximum, can be calculated using this theta s. So to find the axis at which shear stress is maximum, we have to use this equation. It's just the reciprocal of your principal axis equation. Now at this theta s, this is maximum shear stress value. It's quite simple. Find theta p, put for the theta p, get these two stresses, sigma max and sigma minimum. Then find the location of axis at which shear stress is maximum, which is given by this relation, and theta s. And put for this theta s in the equation, you will get the maximum value of shear stress. Now, as we have known, when you are calculating maximum normal stresses, which are nothing but principal stresses, so you won't get shear stress because at principal axis there is no shear stress. But when you are calculating the axis at which you get maximum shear stress, you will also get normal stress at that axis. So that normal stress, we can take the value of this theta, substitute this value in the normal stress equation, so you will get this value. So the normal stress at the axis where you get maximum shear stress is given by this relation, sigma x to sigma y by 2. So these are all analytical relations which we require to find out the stresses at different axes. So these equations are also known as transformation equations. Means you are just transforming your stresses at some other some other axis which has been rotated at some angle theta. So let's discuss now Mohr circle. So whatever I had discussed, that was those were all analytical relations or equations which one can use to find out stresses at some location. Now what about Mohr circle? How to use Mohr circle? Now this man Mohr, what he did, he tried to simplify this complexity. So a lot of equation has to be remembered to find out the stresses, whether it is principal stress or maximum shear stress or stresses at certain angle theta. So he gave a very simplified methodology in the form of a circle. Let's see that. Now also in case of Mohr circle, we need to have some basic values. Again the same, sigma x, sigma y and tau xy. Using this value, we have to draw Mohr circle. So I will just discuss how to draw the Mohr circle. First of all, let's take coordinate axis. Simple. OX and OY are the coordinate axis. Now, for the Mohr circle, the requirement is the x-axis, the normal stress will always act along the x-axis, and shear stress will always act along the y-axis. Again, I will repeat. Normal stress will act along x-axis, and shear stresses will act along y-axis. This we have to remember. This is a very basic requirement of Mohr circle. So we have two normal stresses. So from point O, we will take we will move along the horizontal line, and we'll take a value of sigma x. So this point A has been marked at a distance of sigma x from point O. Still we have one more normal stress. Again, from point O, we have marked sigma y, point B. So simply we are going by the coordinate axis. Let's suppose if your sigma y is negative, if your sigma y is negative, what will happen? It will go on the negative side, on the left hand side. Simple coordinate system. Now what we have done, we have marked 2 points A and B using normal stresses in the x and y direction. Now left is shear stress. Now before you mark shear stress, we must understand the convention of these shear stresses. So as you can see on the slide, just remember very basic convention. If your shear stress is it's making a clockwise couple, take that shear stress to be positive. And if it is making an anti-clockwise couple, take that shear stress to be negative. For example, in this element, you can see on this, if you go with the x-axis, you get a face at which you can find this shear stress. Now this shear stress is opposed by this shear stress just for to maintain the equilibrium, and they both create a clockwise movement. They both create this clockwise movement. You can see, and the clockwise movement is created by these two stresses. So this is the clockwise movement. So it means on this x phase we are getting, this is x phase now, we are getting clockwise. So it means with sigma x you will be taking clockwise shear stress. It means the shear stress will be positive. So once again I will repeat the convention for the shear stress. First look at the face where shear stress is acting. We have x phase, we have 5 y phase. Now if you move along this x, this is x axis as shown in the figure. If you move along this x, so this is the x phase which I am talking about. On this x phase we get this shear stress given to us, it's acting downwards, and for the sake of equilibrium we get one more shear stress on the x phase. It will be just opposite to this to maintain the equilibrium. So this is also x phase. Now they both create a clockwise couple. It means on the x phase, it means if you on the x phase you will get sigma x, and with the sigma x you will get a positive shear stress. Similarly, if you see the y phase, we have one shear stress here and another y phase this one. So this creates an anti-clockwise couple. You can see anti-clockwise couple. So on y phase we are getting anti-clockwise shear stress. So as I told you, just follow the basic convention. If the shear stress makes clockwise couple, take shear stress to be positive. If it makes anti-clockwise couple, take it to be negative. Now in the present case, you can see on the x phase we are getting a clockwise couple. So it means if I take point A, this is a point A. So as I've told you, the shear stress is taken along the y-axis. At point A, this point A is related with the x phase, that is sigma x. Now here the shear stress will be positive because it is clockwise. So that's why we have taken it above the line. I hope it is clear. Now on the y phase, the shear stress is anti-clockwise, so it will be downwards. This is shear stress. So these steps are very important. Once again I will repeat, we started with the coordinate system, and I told you the normal stress is to be taken along x-axis and shear stress is to be taken along y-axis. We started with the normal stress in the x direction with reference to point O along the horizontal line. We marked a point A. Similarly, using the other normal stress in y direction, we marked point B. Now we have to mark shear stress in the y direction. So for that you have to check out if shear stress is clockwise, take it positive above the line. If it is anti-clockwise, it will be negative, take it below the line. From which point to start? If it is x phase, as I told you, if it is x phase and is positive, it is positive with reference to point A, because point A is with reference to sigma x. Similarly, with point B, it is downwards. Now, the requirement of the Mohr circle is join these two extreme points A dash and B dash. Simple. Join these 2 points. Now, taking O dash to be the center and either O dash A dash or O dash B dash as the radius, draw a circle. This is known as Mohr circle. A very important concept, very helpful. I hope it is clear. Now, in this Mohr circle, there are two options. Either you draw it graphically and take some suitable scale and measure all the pixels and find out the stresses, or you can with the given values you can create your own trigonometric relation and find out the values. I will just tell you. In this case, let's first discuss this in the present slide. Now this line A dash B dash basically is your axis. This thing is very important. When you talk about this element, in element we have axes which are mutually perpendicular. Remember that. If this is sigma x and this is sigma y, this sigma x and sigma y are mutually perpendicular. sigma x and sigma y. They are 90 degrees. But when you are drawing a Mohr circle, your axis will be at an angle of twice theta. They will be along the same line. This is the difference. Or the theta on the element becomes twice of theta in the Mohr circle. So that's why this A dash B dash is the axis, is the present axis of your element in the Mohr circle. Now, if you look at this figure and I say, uh, where is the principal axis? And you know, the principal at the principal axis there is no shear stress. So this is only one line. If you take this line OX, along the line OX there is no shear stress. It means this line OX is nothing but the principal axis line. And this green line A dash B dash is your own axis, that XY axis. So it means the inclination of your axis with reference to this black line is principal axis, which is given by twice theta P. This is given by twice theta P. I hope it is clear. Again, this OX is this line is the principal axis line. This is the principal axis rather, and green axis is your axis, X and Y axis. So twice theta P gives you principal axis. Now, if someone say find out this principal axis, how to find out this principal axis? Simply take the geometry. That is all. Apply trigonometric ratios, apply algebraic relations, and you can find out the values a very simplified way in a very simple manner. I will take an example. Okay, first we'll discuss that. Now, what is the maximum principal stress? Just see this line from O, from point O, that is the origin, to the farthest point on the circle. The farthest point is this point P. This point P is the farthest point. So this blue line you can see, this gives you sigma max. Similarly, what is sigma minimum? The closest point. So this is the closest point. This gives you, OQ gives you the minimum stress. So that is how from the geometry we can know the stresses. It's quite simple, much simpler than remembering all the analytical relations. Now, if I say another question, what is this axis? Now, what about maximum shear stress? Now, you know, vertical line means vertical line is nothing but the shear, and the maximum shear stress, maximum vertical line you can get here. You can see this point. So, obviously, this gives you maximum shear stress. Now, how to find the inclination of this maximum shear stress with the axis of the body, or x and y were your initial axis? So this we'll discuss again while doing some problems. So about this x, at what axis I will get maximum shear stress? That will be theta s, if you can recall, theta s. Now in this case, this green line is your x and y axis, and this becomes your theta s. So this we have to discuss in detail also. See, geometrically you can find out any damn angle, but you have to remember that what parameter is represented by what line. That is all. This thing is to be remembered in Mohr circle, and then simple calculations. So let's move further. Let's take an example. I hope now it is clear that you know how to draw a Mohr circle and what point gives you what. So this is an example. It says following stresses are acting on an element. So stress in the normal direction is tensile since it is positive. Stress in the y direction is negative. It means it is compressive. And shear stress is given to us. It is a positive shear stress, 45 megapascal. So before I start, once again, I would like to discuss here. It's very important. Convention for the Mohr circle is quite different. I just told you clockwise positive and anti-clockwise negative. But when we talk about this shear, here shear is given positive. So what do we mean by this positive shear? Just remember those simple axes, x and y. Let's suppose if you are moving, positive shear means tau xy is positive. So there are two conditions. If you're moving along the positive x-axis, as I'm showing here, and you get a face here, say this is a face, I'm not drawing the whole diagram, this is a face. You have moved along positive x-axis, and on the face you get a positive shear in the y direction. So both are positive, it becomes positive. That's how we mark positive shear stress. Similarly, if you are moving along the negative x-axis, let's suppose this is minus x now. Let's suppose it, and on this face here, on this face, you get shear in the minus y direction. So it becomes what? Minus into minus plus. Again, it becomes positive shear. So that is how you have to analyze. This is I'm talking about just to mark shear. Okay. Now, what has been said in this example is, he says, draw the stresses on an element. So means you have to show the stresses on an element first, and then determine the following using transformation equations and Mohr circle. It means, he says, you make use of those analytical equations, solve all the parameters which has been mentioned, and the same is to be repeated or calculated using Mohr circle. So it's good. We can get more clarity. So these parameters are to be determined. Let's see what are these parameters. Now, principal axis. Once again, I will just brush up. You have to find principal axis. It is nothing but the orientation, inclination of the axis. So that theta p is to be determined here. Then principal stresses. Now you know what is principal stresses, sigma max and sigma minimum. So then come plane of maximum shear stress. So it becomes plane of maximum shear stress. So let me write here. It is theta s. Now you can remember that formula also. You know the Mohr circle also. Then tau max, maximum shear stress. Then normal stress at the plane of maximum shear stress, means at theta s you have to find what is the value of normal stress. Then the last part is you find normal and shear stresses acting on the element when it is rotated 30 degrees counterclockwise. It is somewhat generalized. He says, give me the value of all the stresses when you rotate your element 30 degrees counterclockwise. So these are the parts which we need to determine. So first of all, we have to show the stresses on an element. So as I told you that that sigma x is tensile, sigma is compressive, and for shear stress, I told you how to take positive shear. So here comes the element. As sigma x is tensile, sigma y is your compressive as shown. Then tau xy is positive, as I positive plus x and plus y. This is positive tau xy. In this case, minus x and minus y, it becomes again positive tau xy. Same is the case with the y face also. Now let's start with the exact problem. Let's find principal axis. Now mind it, we will be using all those transformation equations. Principal axis. So this is the formula. Put for the values of sigma x, sigma y, and tau xy since they are given to us. So once you substitute all the values and just check it, the sigma y is negative. So you have to use that minus value. So here we get principal stress, the angle, the inclination of the axis, or the direction of principal or location of principal axis is 23 degrees, because there are two axes on an element at 90 degrees. So 23 plus 90 becomes 130. So these are the values of principal axis. It means we have calculated that value when theta is positive 23 degrees. So you will get there will be no shear stress, and the normal stresses will be maximum. So next is the principal stresses. Yes, simple relations. Sigma max and sigma minimum. Put for all those values. Now these are the values. The sigma max is 94.08 megapascal, and sigma minimum is minus 31.08. So again, it is negative. Now always, whenever you're dealing with such problems, always show the stresses on element. So always try that for better clarity. As an example, so this is the basic element with us. Now we have to show the stresses on the new position of this axis. when the element has been rotated at an angle of theta p. Now, one more thing I would like to mention here. Actually, the rotation is of the axis. Practically, the element is not rotating, but just for the sake of understanding, we just show that rotated element. Practically, if you see any machine part, uh, as an example, I will try to show it here. Let's suppose this is a shaft, for example. This is some sort of a shaft or a machine component, and you need to find some stresses. Let's say this is subjected to some tensile load, some loading. It's a huge shaft. So we have to analyze being a designer. So I will take a small element in this. So this is what we are discussing. This is a small element, and this element is that element only. So it must be having some axis, x and y axis. So because of certain conditions, the load might get shifted. The load might act at some other angle, because when the machine is on, when the vehicle is moving, the wear and tear will take place. The the action of the line of action of the load may change. So what we try to explore all possibilities and find out the maximum load acting on that element. So that way we show that we show that at this angle what is the stress. We go on calculating the stresses at different angles. And yes, at the principal axis we know that we get principal stresses and maximum stresses. So what I was telling you, that rotation of element has been shown for the simplicity. So there shall be no misconception. Now what we have shown here, we have to show the new stresses at new position as shown here. Theta p is positive above the line. So at this theta p, we get maximum principal stresses. There is no shear stress because these are the principal stresses. So sigma max tensile, sigma minimum compressive, because we are getting this negative value. I hope it is clear how to show the stresses. So every time whenever you use analytical equations, try to show the stresses on that element. So let's move ahead. Now what else is to be found out? Other part is plane of maximum shear stress. Now you can recall that formula tan twice theta s. Simply use that formula. Put for the values. Let's see. We get theta s is coming minus 22. So or plus 90 is 68 degrees. So minus 22 means below the axis, you can say. So again, now what was the next part? We have to find out. Okay, let me show you that there is a relation between the axis, the principal axis and the maximum shear stress axis. So they are related by this angle. So this theta s is equal to theta p plus 45. So that way also I have shown you here. Try to calculate that. It is one and same thing. 68 here, also 68 here. Because they are related. You can see the relations of theta p and theta s. Relation of principal axis and of that maximum shear stress axis. The next part is maximum shear stress. You remember that formula. Put all the values, and this is a maximum shear stress, 62.58 megapascal. Now, what next? We have to find the normal stress at the plane where you get maximum shear stress. I mean normal stress at theta s. Let's see that. Normal stress at the plane of maximum shear stress. So this is a generalized relation. I've just tried to show you from the basics. Now theta s, replace this theta by theta s. Simple. I've replaced this theta by theta s. We know our theta s was minus 22. I have simply substituted that 22 here. So this is what we get. So normal stress at the plane of maximum shear stress is 31.5 megapascal. Also, you can remember. So this you can remember. I substitute all the values, we get this relation basically. The normal stress at the plane of maximum shear stress is nothing but some sort of average of the normal stresses, sigma x plus sigma y by 2. So even if you remember this relation, so that's more than sufficient. So I would have straight away taken this relation to show you, but the best part is to let's work out in detail. You should know how these values are coming. So next part was, okay, let's show this on the element. This we have not shown yet, because now we have calculated the stresses at theta s. Again, the initial element is shown to you. This you already know, theta p. And as it is shown, to add theta p plus 45 is equal to theta s. The relation between shear stress axis and principal axis is it is theta s equals to theta p plus 45. So this becomes your look position of your uh, this becomes position of your maximum shear stress axis. So at maximum shear stress, yes, it's tau max, but at this we will get some normal stress also, which has been shown here with that star superscript. So this is how you symbolize this element. Now this 22 degree, now I have shown here theta p plus 45. Now you must be thinking, what is this? Where is this 22? What would 22? Now as I've shown you, theta s is equal to theta p, if you don't go that way, plus 45. Just remember, it's very simple. This is here. Now if theta p was you add 45 to it, so you get this value, because we have, as I told you, when you talk about these elements, we have axes at 90 degrees to each other. So that way we can find the minus 22 also. In case of minus 22, it is to be taken below the axis. So minus 22 plus 90 becomes 68. This is 68. This becomes 68. So it means from this axis, this is my shear stress. This is tau s, sorry, theta s plus 68. And if you take minus, you have to take it below the line. It will be your minus negative value, minus theta s. So that is how we calculate the normal stresses at the plane of maximum shear stress. So let's brush up what we have done so far. First, principal axis, that is theta p. Then principal stresses, sigma max, sigma minimum. Then next, the maximum shear stress, that is theta s. Then the value of the maximum shear stress. Again, we can use that relation straight away. Then the normal stress at the plane where you get maximum shear stress. So that's what we have done right now. So last part, it is the normal and shear stresses at the new rotated plane, which is at 30 degrees to the initial axis. So we have this relation with us. It's quite simple. You have this relation, put theta is equal to 30 degrees. You have the value of sigma x, sigma y, and tau xy with you. Go on putting all these values. So you can find out the stresses, the normal stress and the shear stress. You can see. So these are all values. So that is how we calculate. We get the normal stress at the new position 92.22 megapascal, then 29.22 megapascal, and shear stress is minus 15.17 megapascal. So that is using these transformation equations. So we have calculated all the parts using transformation equations. Now we will repeat the same using Mohr circle. So let's see. Okay, first we'll draw it. Again, I've just skipped. Now again, theta is there. Let's draw the element. So this is the basic position. And now at 30 degrees, rotate your element and show the stresses. Always do that. Now going to Mohr circle. Again, for basic stresses we have with us. Let's draw Mohr circle now. First, take axis. As I told you, the horizontal axis will be created by normal stress, and the vertical will be created by your shear stresses. Don't forget that. So sigma x is positive. First, let's mark sigma x from point O along the line OX. Point A, this is sigma x. Then sigma y. Now here your sigma y is negative, so it will come on the left hand side of this region O. This is sigma y. Now we have point A and point B. So next is the shear stress. Now I have already told you the convention. If it is clockwise, take it positive. If it is anti-clockwise, take it negative. Now on the x phase, this is your x phase. X phase, you can see here, it is anti-clockwise. You can see on x phase it is anti-clockwise. It means it is negative. So it has to be marked below the line. This is below the line, A dash. Now similarly, on the point B. In point B, you can see it is clockwise, so it will be above the line. Now what next? Joining these 2 points, A dash and B dash. Let's join these 2 points. This green line is your axis, X and Y axis, denoted in Mohr circle. Now take O dash as the center and O dash A dash as the radius, or O dash B dash as the radius. Make out a circle. So this is the Mohr circle. Now using this Mohr circle, you have to find out all the parts. So let's do that. So as I told you, either you can draw Mohr circle graphically, or the best part is draw it proportionately and using the given dimension, given lines. For example, this AA dash is tau xy. This OA is sigma x and OB sigma y. So using these given values, if you can find out all the sides, that is of more worth. That's of good worth. This will be of great worth. We can get all the values. We can calculate every parameter. What we have done with the analytical equations. So let's see. For example, if I say what is this value, O dash A equals to. So you will say that it is nothing but sigma x. That's OA minus this O dash A minus O dash A. What is this O dash A? You can think for a while. What is this O dash A? It's quite simple. This is nothing but because this AB has been bisected by this A dash B dash. It means O dash A is equal to O dash B. But what is this OA? How to find this OA? So this we have. This is sigma x. Okay. This is sigma x. I will just draw a line to show you here. Sigma x from here, sigma x, and this is sigma y. Sigma x plus sigma y. It means AB has been bisected by 2. So it becomes sigma x plus sigma y by 2. So this O dash A or O dash B gives you sigma x plus sigma y 2. So likewise, you have to calculate all the values. It's quite simple. So let's check out. So yes, this is the principal axis as I told you earlier also. Now I think you can find out principal axis now. You can take this right triangle O dash A dash, tan twice of theta P is equal to perpendicular is A dash divided by base O dash A. Simple. So let's see now. As I told you, this is the value 43.5. So let's find out principal axis. So this value I have shown here. Now OO dash, this one, OO dash equals to what? That is nothing but sigma x minus of O dash A as shown here. So it means we get the value of O dash is 31.5 megapascal. So geometrically, you have to find all the values. Radius, use Pythagoras theorem. You know the value of O dash A, you know A dash, use Pythagoras theorem and find out radius. So this is the radius. Then the principal axis. Take right triangle O A dash or O dash B dash, any of the right triangles. So this is also principal axis. This is also principal axis. Take this right triangle, put for the values. See, you get the same value, 23 degrees. If you can, you can recall what values we have calculated using analytical equations at the same value. So this was the first part, principal axis over. Now what about next? Next is the principal stress. So let's see how to find that. So first is again draw the basic Mohr circle. This is the basic Mohr circle. Now on this Mohr circle, which line gives you principal axis? From the origin, the farthest point, as I told you, the farthest point is this point. This is the farthest point. It will give you sigma max. And the other point, this will give you sigma y. Two extremes you have to cover. Okay. This blue line gives you sigma max, that is OP. Now, how to calculate OP? It's simple. OP is equal to OO dash, which is known to you, plus a radius. That gives you sigma max. Let's see. Similarly, sigma minimum. So principal stresses, the sigma max, as I told you. So you just add radius and subtract radius, you get both the stresses. See how simple it is to work out with this Mohr circle. Now, what is the next? Maximum shear stress. Yes. No, where is the maximum shear stress? And remember, shear stress is given by a vertical line along the y-axis. The maximum point, as shown here, this line CD, nothing but line of shear stress. Either you take point D or you take point C. So this gives you maximum shear stress. So how to find maximum shear stress? That's the radius. Tau max is OC. It's the radius, simply radius. So it's direction. We have to find its direction also. No? You have to find out the angle. If you can recall that theta s. Now, which line gives you theta s? Plane of maximum shear stress. Now, this green line is your axis. Don't forget this green line. This green line is your xy axis. This green line is your xy axis. Don't forget it. With this green line, you have principal axis. Now, with this green line, you have this maximum shear stress also. See in the figure. This is twice theta s. Now, you must be wondering how simple it is. Now, from the geometry, you can find out. If I take 90 minus of twice theta p, I get twice theta s. See here. So how simple it is. It is 22 degrees. Within no time, you have calculated the plane of maximum shear stress. So let's move ahead. Let's find out other parts also. Now again, the basic Mohr circle I have shown here. What is to be found out now? Now see, what is this twice theta? If you can remember the last part, you have to find out the stresses at when the angles are rotated counterclockwise at 30 degrees. And I have told you, when you are working with Mohr circle, you make twice of theta always. Just remember it. Theta with the element, and when you come to Mohr circle, make it twice of theta. So we have taken twice of theta counterclockwise with your axis. As I've told you, the green line is your axis. Now this green line basically rotates. Your axis is rotating only. So this A dash B dash position will get changed. So what it becomes? So okay, let me show you. So okay, let's see here. So this becomes, this is new position, A double dash B double dash. So your body axis, that's A dash B dash, has been rotated to a new position, which is at an angle of twice theta. So this is A double dash B double dash. Now it says find out values of the stresses. Now that you can do, because we know what is the which line gives you the normal stress and which line gives you the shear stress. On the horizontal line, you will get normal stresses, and on the vertical line, you will get shear stresses. Now see, always check out this rotation. This A dash point, this A dash point is with sigma x. Now this has been rotated here to A double dash. So it means if I take this distance, if I find out this distance from here to point A, what it will be? You can guess what it will be. It will be sigma x star or double dash. That is the normal stress. Okay, let's see. So from here we have drawn lines perpendicular on the x-axis. Now it is very easy to understand. You draw all of the lines and find all the values. So I will just try to show you here. This line gives you the sigma x, that star, if you can recall. Star means a new position. You can take star dash something just to differentiate. We have taken this star. Similarly, with reference to the other point on the Mohr circle, you can see point E. It gives you sigma y star. So you have to calculate these values. Then the vertical line A double dash D or B double dash E, it gives you the shear stress as shown here. Now you have to calculate these stresses from the Mohr circle. So that you can do very easily. So let's see what is sigma x star equals to. Because you know what is O dash, what is O dash D, what is radius. Now you already know these values. You have already calculated these values. So let's see. Sigma x star, this value is given by OD, and OD is nothing but OO dash plus, you can take this right triangle, O dash D A double dash. You can take this right triangle. In this right triangle, this O dash A double dash is the radius. I'll just try to show you. This line is the radius. Now this line is the radius, and I can take this right triangle. Now in this right triangle, we have to find this angle. Now you can see this angle is nothing but because this total was twice theta, as I told you earlier. You have rotated your axis. The green axis has been rotated to new position. So in this right triangle O dash D A double dash, this angle becomes twice of theta minus of twice of theta p. It is 14 degrees. Now that angle has been shown here. This 14 degree basically is that angle. It has been shown here. So from this you can find out all the values you can find out. So it becomes O dash plus O dash A. This R cos of 14 degree gives you this 92.2. New value of normal stress in the new direction with the x-axis. And similarly, if you minus that this R cos 14, what you get? You get the uh, value of your other stress along the y-axis. So that has been shown here. You can see sigma y. Sigma y means this is sigma y. It is OE. Now what is OE? Again same. This angle is also 14 degree. This is also 14 degree. This is 14 degree. Now again radius cos of 14 degree minus of OO dash, and this we already know what is OO dash. This we have calculated. So similarly from this right angle you can find this value of shear stress also. So that is how we can calculate all the stresses which we have already calculated using transformation equations using Mohr circle. And it is quite simple to use Mohr circle. You don't need to remember heavy equations. Simply you should know which line gives you what value, and accordingly you can proceed. So I hope it is quite clear to you how to draw the Mohr circle and find out all the values pertaining to your stresses. So thank you very much. See you again.